So hello everyone and welcome to this next lecture in the DC-DC converter video series, and so far we've been simulating the transformer. So this is where we had left off in the previous lecture. More specifically, we had simulated a transformer and we had arrived at an unstable result. Now in this lecture we are going to continue and try to debug that the unstable result. So before I start this lecture, a little bit of brief background. That if you are interested in these kind of online video lectures, but you would like something a little more comprehensive, I do have a full-length online course on the MOOC website Udemy. The first course which I have is called Simulating Power Electronic Circuits Using Python, and in this course I talk about the basics of Python, how to install the software, how to install Python Power Electronics, some basic power electronics, and finally a case study of simulating a buck converter. The second course which I have is more on the signal processing and control side, and that is basics of digital signal processing for power engineers. And in this course I talk about the basics of signal processing, how to design filters, how to analyze the frequency response characteristics, and finally there is a case study in which I design a low pass filter and a notch filter using frequency response characteristics with NumPy and SciPy packages. And the last course, or the latest course which I have, and probably is the most relevant for this series of lectures, is simulation of magnetics for power electronics using Python. And in this I talk about how we can simulate inductors, coupled inductors and transformers using Python power electronics. And finally there is a case study of simulating a flyback converter. So with this course, with this background, I will get back to the lecture. So, as I said before, we go back to our code, right? The most important thing here is we need to figure out why things are unstable. Now, we tried a few things, right? We did try a few things, like, for example, whenever you are faced with instability, one of the most natural things to do is to decrease the sampling time step, right? Now, unless there is good reason to believe that this sampling time step is indeed, or rather integration time step, is indeed too small, you would not want to decrease this too much, as it slows down your simulation, right? So, for example, we are simulating a 50 Hz transformer. If we are simulating a 50 Hz transformer, a 1 microsecond integration time step or a sampling time step is very acceptable. So there is no need to actually decrease this further. Later on, when we actually start simulating flyback converters and forward converters, we would have to decrease this because our frequency has increased, and therefore the transformer frequency would also increase. But for 50 Hz, this should be enough. Therefore, even though it is tempting to actually decrease this, I would not decrease this. Decreasing this will just slow down your simulation. We need to find other solutions, right? Now, let's continue. Now, we already saw that in this simulation, it was working. There was a marginal instability, and now it is completely unstable. Now, when you are faced with this kind of changing stability, that is, a system that was stable, became marginally stable, and then moved on to completely instability, the most common culprit is the model, the simulation model of what it is you're trying to simulate, and in this case, it is the transformer. So for example, this is our simulation model, right? This is where we are actually calculating. So we are calculating the induced EMF from the applied voltage and the currents that are already flowing in the transformer. Using that, we are integrating it to calculate the flux linkages, and here we are calculating the currents, winding currents. So now the question is there a way to actually make this better? So for example, let me just clean this up. This is an old equation where I was using the magnetizing inductances. We don't need that anymore. We are using the mutual inductances. So these are the equations of the flux linkages with respect to the currents, right? Now, in order to solve this simultaneous equation, we had now used this method. That is, we had expressed I1 with respect to I2 and then substituted I1 in the other equation, that is the second equation, to find out this current I2, right? Now, this is just simple substitution. Now, the question is, this model was working and now has stopped working, and there was a period of instability. So the question is, is there a way in which we can actually calculate this in a better manner? That's the question we need to ask. Now, mathematically, there is nothing wrong with it, because all we did was we did a process of substitution, right? But the question is, if you look at this equation, most importantly, let me just give it a space so that I can focus on it. If you look at this equation, we are expressing I2 with respect to the flux linkages of winding 2, the flux linkages of winding 1, the current I2 itself, and the rest are constant, the inductances, right? The problem is we are now calculating the present value of this secondary current, but in this equation we are using the previous value of the current as well, right? Now, there is nothing really wrong with it, and in many cases you would have to do it. But now always we need to ask the question, can we find a better way to do this? So for example, if I were to write this equation and I were to expand it, so let's say for example, just going to copy these terms. So instead I'm going to say psi1 plus m12, basically it's m12 squared, so I'll just do a multiplication here into I2, and this entire thing is divided by L1, so it's m12 multiplied by psi I2 L1, and m12 squared multiplied by I2 divided by L1, and the entire term is divided by L2, right? This is what we have. All I have done is open out this bracket, right? So now the question is, can we take this term and move it all the way here, right? We should. So supposing for example I say I2 and this is a negative sum, so if I take it to this side, on the left hand side it will become positive, of course. So what I'm going to, no, actually that is wrong, it is minus, because you see there is a positive term here. So let me just take this, copy it, put it here, and we need to adjust this to make it L1 multiplied by L2, right? That's because there is this term L2 here, right? This is just simple substitution. I'm not doing anything in power electronics or magnetism or anything. This is just equation solving. So all you have to do is expand this equation, bring it over to this side, and finally simplify it. So there is nothing electrical engineering here. So I can just copy this to make it easier for myself, and let me delete this term because this term has been removed, and the remaining terms can stay, right? So all I have done is I have taken this I2 term out from here, moved it to the left hand side, and left only the known terms here. See, psi I2 and psi I1 are being calculated here. They are integrals of the induced EMF. Therefore, these are known terms. There is no unknown term here. Now, all the unknown terms are on this side. So, if I want to now simplify further, what do? Now, I would say I would delete, or rather I would copy this, right? I would copy this and I would bring this term over to this side, right? So for example, all I say is I leave this term here, right? Everything stays exactly as it is. The only thing that is going to change is I'm going to bring this term from the left hand side to the right hand side. So you just multiply. Okay. Again, there is no power electronics here. I'm just using simple substitution. And let me just copy this. And let me get rid of this I2 term. So this is our equation, right? Let me just verify. I'll just take this out, copy it, give it an indent, right? And let me just verify, most importantly in these kind of equations, you need to verify if you got your brackets correct. Now, this is the closing bracket, that is right. This is the closing bracket, that is also correct. This is also correct. And so is this. Alright, so the brackets are correct. So just a quick recap. All I have done is I have opened this expression out, taken out the I2 term, taken the I2 term to the left hand side, and resubstituted it to create a new term for I2 which is devoid of I2 on the right hand side. So I2 now depends only on known terms psi2, that is a flux linkage of winding 2 and the flux linkage of winding 1. So with this, what I would do, I would comment out this. This can stay as it is because there is nothing here. All I have to do is substitute the value of I2 here and calculate I1. So this can stay as it is. But I'm going to use this new equation of I2 to calculate the winding current in I2. Right? So with this, let's go over to the simulation and let's run this simulation. As always, let's go to the command line, make sure there is no error. There is none, so we are good to go. And here let me click on the winding voltages. And now it is working. Right? You see, now this is working. So therefore, we have solved our instability problem. Let me just click on the transformer currents as well. And these two are working. So we have solved the instability problem that we faced in the previous lecture simply by resolving the equations or expressing the equations in a different way. The main reason for the instability was that because I was using, that is in this equation, because I was using this, rather let me just separate this. I was using this equation before. These were the older equations. Because I was using this, I was using the previous value of the winding 2 current in calculating the present value. By doing so, I was introducing an inaccuracy, right? This inaccuracy eventually blew up to result in instability. That's essentially what happened. By eliminating this equation, eliminating this term from the right hand side completely, now my calculation is devoid of the previous value. It is only using the present value of variables because psi I2 is only using the integral of the voltage, right? This is how you look at instability. This is how you look at potential ways to improve the accuracy of your model, right? You see, it was exactly the same equation. There is nothing different in the equation. It is just changing the terms and moving the terms around, right? So with this, let me just go over once and let me plot it again. Get a few more cycles, make sure that the system is stable. And yes, it is. So with this, we have now our winding voltages. As before, since we have a 2:1 step down transformer, the primary voltage, which is the blue line, is twice the secondary voltage, which is the orange line, right? Now, if you look at the transformer currents, we see here that this is the key. So therefore, the blue line is the primary current, the orange line is the secondary current, right? And here, of course, you do see that even though the secondary current is larger, because remember, the low voltage winding will have higher currents, the higher voltage winding will have lower currents, right? So since we have a step down transformer, the secondary winding, which was lower voltage, has a higher current, right? But still, we do see that even though we are, let me zoom in on this because it's not very clear, between 2 and 5. So let me plot this between 2 and let's say 6. Just to make sure that we have the same ratios or similar ratios with respect to the currents as well. So here, now you see that the currents the primary current has a peak. Actually, let me zoom in even more. Let me zoom in between 5.1 and let me zoom in from 2 to 5.1, 5.2. Surprisingly, I think I closed down my file browser. And these are the transformer currents. So, you see that the current peak is around 3, right? Or rather, the primary current peak is around 3. The secondary current peak is around 5, right? Now, here again, the question is, what could be the potential reason? Now, one reason for this is, as I said before, the magnetizing current. And to know about the magnetizing current, what I would do, I would just go stop, go back to the main page, edit the circuit parameters, and increase this load to a large value. So let's say I'll make it 5000 ohms. And let me run the simulation again. As always, go to the command line, make sure there is no error. We're good to go. And let me plot this again. Okay, so it is just starting. Maybe I should wait for a few seconds before plotting it again. So we have something. Now, the question here is, you see, the blue line is the primary current, the yellow or orange line is the secondary current, and you see that the secondary current is almost 0, and that is expected. The reason for that is because our load resistance is very large, so we have a very low load. But even in that case, the primary is drawing this almost 0.75 ampere current, right? It's almost 0.75 amperes. I could zoom and have a look. But this 0.75 amperes current that is drawn by the primary, even when there is no load or negligible load, this current is the magnetizing current of the transformer, right? And this magnetizing current is the reason why we did not see an absolute 2:1 ratio in the currents. The reason, because the primary current is still containing the magnetizing current as well as supplying the load current, right? So with this, I will end this lecture. We have been able to solve the instability problem that we experienced in the previous lecture, and we have also looked at the magnetizing currents in a slightly better way. So with this, we can say that we have a working transformer model, but of course we might always have to change our model as time goes on if for some reason, that is, our circuit needs a more complex model. So if you have any doubts about what I did, feel free to send me an email or post in the comments or message on social media, and I'll be happy to respond. Otherwise, I will see you in the next week, where we will start with looking at the high frequency aspects of a transformer, or rather looking at how a transformer can operate in applied with high frequency voltages. So thank you so much for watching, and see you soon. Goodbye for now.